Hello, I am Patrick André. I'm an EMC consultant in Western Washington, and today I'd like to talk with you about EMC bench testing, specifically the DO-160 sections 16, 18, and 19. So let's jump right in. In DO-160, as well as in MIL Standard 461 and other standards like MIL Standard 704, there really is no requirement to have a certified lab perform your testing. So many companies actually perform their own testing at their own facility. This is true for MIL Standard 461. However, there is requirements that the lab must meet in order for you to perform the testing correctly. And those requirements are spelled out in Section 4 of MIL Standard 461. Now, as far as DO-160 and MIL Standard 704 are concerned, bench testing does not need to be done inside a shielded enclosure. The bench, if used, must be of a certain size and of a certain material. So it has to have a square footage of at least 2¼ square meters. And also it has to be of a certain conductivity. Now, most people will use a copper bench, but that's not necessary. You can use aluminum, brass, or steel as long as it meets their conductivity requirements. Now let's look at the specific tests here. DO-160 section 16, we'll start there. That's an input power test. Now the input power test that is performed is only on the primary power to the equipment that you're testing. These tests are in a variety of styles. They're over voltage or under voltage tests where you have to dwell at a specific higher or lower voltage and still operate correctly. There are various types of dropouts. Specifically, say from on a 28 volt power line, you have to drop out down to 0 volts and then back up to 28 volts. And the dwells of the dropout can be of various lengths, 50 milliseconds or whatever. And there are ramped or momentary interruptions. And there's, for some types of digital circuits, you may have to do a double dropout. And we'll look at some of these types of waveforms here. In the double dropout, the testing is actually performed twice, with the two dropouts either separated by either 10 milliseconds or 50 milliseconds. There are surge or over voltage type of tests where the equipment has to be stressed to a very high level. Say on a 28 volt line, there's one test to a specific category where you have to actually dwell at 80 volts for 100 milliseconds and then drop down to 48 volts for 1 second. And that is done simultaneously. First 80 volts for a tenth of a second and then 1 second dwell at 48 volts before you can return to a normal 28 volt line. And there are other tests such as engine starting where you'll initiate the voltage at some low level, 10 volts DC for example, and slowly increase that to 20 volts or 20.5 volts over a period of 35 seconds. Now for this type of testing, there's no requirement to have a ground plane, although it's acceptable to use one. The one thing that we recommend though is never to use an LISN on the power lines when you're performing this testing. And the reason why is that the LISNs can actually distort the waveform and create an unfair advantage or possibly a disadvantage to the equipment. Now, in the revision of DO-160, DO-160H, which will be coming out likely next year, LISNs will be specifically prohibited from being used in Section 16. Now let me look at the DC momentary interruptions test in particular here. And this is where the AE Techron equipment really excels. In this test, you have a dwell time at your voltage, in this case 28 volts, let's say, and then you drop down over a specific period of time, dwell at some voltage level, and then increase over another specific period of time. And here are the test requirements that might be required of you, depending upon which category you're using, A and A and B eliminates some of these tests. Let me look at this first one in particular, test condition 1. It says you have to drop in less than 1 millisecond, and then you have to dwell at that voltage for less than 1 millisecond, and then you have to rise from that 0 volts, as it turns out, up to full level in 2 milliseconds. Well, this can be a bit of a challenge if you have to try to manipulate these voltage waveforms very specifically. This is where the AE Techron 3301 excels. I performed this test for a client, and this is the waveform I was able to generate. In the fact that I needed to drop in less than 1 millisecond, what I did is I programmed it for 900 microseconds. So from this point here down to this point down here is 900 microseconds, and it comes out very, very precisely. I then dwell at 0 volts over this period of time for, again, another 900 microseconds, because it's intended to be less than 1 millisecond. But then I have to rise in 2 milliseconds back to full voltage. And you will see here, I put some markers here from this point to this point. If you look at up here, it says the delta time between those two markers is exactly 2 milliseconds. The voltage starts at 0 volts. I've got it just a little bit off the peak there, but it's 27.8, almost 28 volts. Precisely performed and exact to the requirement. This makes your testing super simple to be able to do these waveforms. If you need to modify it for any reason, you can go in there and change these parameters very quickly. Now let me move on to section 18, the audio frequency conducted susceptibility test. This is actually called out partially in section 16 as well as a voltage ripple test. And the intent is that your equipment must operate with a voltage ripple on top of whatever voltage you're operating at. The test is, this is actually a very slow test because there's 30 frequencies per decade, so you have to do 30 test frequencies between, say, 100 hertz and 1 kilohertz, and they have to be logarithmically spaced, and they have to have dwell times that are very long. Now let me go to the next slide here. So you're dwelling at each of these frequencies for 60 seconds. Now the test starts at something like 10 hertz and goes up to 150 kilohertz. Well, that test is going to require 2 hours and 7 minutes at 60 seconds at each specific frequency. And maybe longer if you have some settling and dwell times at each frequency. So historically, this testing has been very, very slow. Now the test also has typically required the use of a isolation transformer. Well, there's one I've placed right here. And this is similar to the T2000 that AE Techron carries. So you have your signal generator, your signal source, say the 3110, and then you have an amplifier of some type. You drive it through the audio isolation transformer. Now you, at that point, are to measure the amount of current that you're generating, and this is a current separate from the input current to your unit. This is the AC current that you are coupling onto the line. And you also need to monitor how much voltage is on that line to assure that you're obtaining the test requirement. Now the current system will require a pre-calibration to be performed in order to assure that these levels are being tested adequately, that you're reaching both the voltage or the current, or that if one or both are exceeded, the total power you're injecting into the system may be higher than, say, 80 watts, which at that point you can start backing off the power. You don't have to drive more than 80 watts into your system. We're not trying to cook your equipment. We're just trying to test to make sure that it isn't susceptible to voltage ripple. What you're going to find out after our presentation here is that there's going to be a new system that AE Techron has developed, which has feedback in this regard. It will monitor the current, it will monitor the voltage, and assure that you are reaching one level or the other. And if you are over testing, if you're putting too much power in it, it will back off that level automatically and allow you to test without over stressing your equipment. I really am looking forward to this new piece of equipment that's going to be coming out. Now, I am on the RTCA SC 135 committee that is in charge of updating DO-160. And I asked this question specifically to some of the people on the committee. Is there a reason why a voltage ripple cannot be just placed on the power line? Does it have to be transformer coupled? And the answer is no, it does not need to be. You can drive straight from the Techron 3110 into your amplifier and to your unit, placing a voltage ripple on top of, say, the DC or AC power that you're supplying to the equipment. That means that at each frequency, you can test to whatever voltage you might want, under test or over test as required or as appropriate for engineering purposes. And it would be a lot simpler in this particular case to make modifications, to set up the test, and just induce a voltage ripple into the equipment to assure compliance over the frequency range that's required. Finally, let me look at section 19. Now, section 19 involves 5 different tests. There's magnetic field tests and there's electric field tests. There's also a spike test we'll discuss. These magnetic fields and electric field tests are either induced into the equipment or into the interconnecting cables of the equipment. Now, this test is not required of power lines. We are not injecting or inducing signals onto the power lines. Those tests are all dealt with other sections of DO-160, specifically the audio frequency conducted susceptibility, section 18, will stress those power lines much more so than this test will. Now, there are 4 different categories that your equipment may be subjected to. One of these 4 categories are going to define what test levels you're going to have to meet. You're also going to have 3 different aircraft primary power sources. C would be 400 cycle, N would be 350 to 650 hertz, and W would be 350 to 800 hertz. Now, I want to make this clear that this doesn't have to do with what power your equipment is taking, but what is the primary power on the aircraft. Here's why. Maybe you're operating at 28 volts. Well, why do you have to do any of these tests then? Well, the reason why is that the aircraft, in this case, let's say it's has a category W type requirement. The aircraft uses power somewhere between 350 and 800 for a variety of equipment. Well, those cables are going to be routed around the aircraft, and they may be next to your interconnect cables. If that's the case, that power, 350 to 800 hertz, can couple onto your interconnect cables. And that's where the interference may come in. So it doesn't have to do with what primary power you're using. It has to do with what's the primary power that's actually used on the aircraft. Now, once again, we're going to perform sweeps, frequency sweeps over defined frequency ranges. And they're going to be 30 frequencies per decade, logarithmically spaced. These dwell times are actually 10 seconds per frequency. So some of these tests can be a bit faster. And many of these frequency ranges are much shorter than they are for Section 18. So testing may be in the realm of 5–10 minutes or so. There is the ability to reduce the test level when you know that your installed cable is less than 3.3 meters. So your interconnect cable now goes from your device to some other device. And on the aircraft, it is known that that cable is only 2.8 meters, let's say. Well, in that case, it's only 2.5 meters that would need to be tested. You can use a 2.8 meter cable, and I'll show you why it's only 2.5 meters in just a moment. This test is also not required if you have very short cables. So if from your unit to an adjacent unit is less than 1.5 meters, you don't have to perform this test at all. You're excluded for that cable to be tested to Section 19. So let's talk about the individual tests. This is the magnetic fields induced into the equipment. This is going to be performed by placing a current in a wire, 20 amps of current, over a specific frequency. And maybe it's 400 cycles, maybe it's somewhere between 350 and 800, depending upon the test. Now, the requirement is similar to other Section 18. These frequency spaces are about 8% apart. They're 30 frequencies per decade. Well, that's not quite a decade of testing, but so you'll do a few frequencies at least. And I always recommend, whatever you do, always dwell at 400 hertz as one of your test frequencies. It's just a good practice to assure that you're not skipping across 400 hertz. You're also going to perform this test by sweeping the wire up and down on each face and side to side. So you're doing it in two polarities, left to right and top to bottom, let's say. Or in the case of a top face here, you'd be doing the wire this way and the wire this way. Since you also have to do it over a number of frequencies, it might be easier to have the wire in one location, 15 centimeters apart from the unit, and run through the frequency scan and then move it over a bit. So maybe 2 or 3 positions across the top face or 2 or 3 on the side, and you'll get through it fairly quickly. So there's not a lot of frequencies that you'll have to test. But one thing I do recommend is you can handhold this unless your piece of equipment is very large, and then you may have to place this on some sort of like pole or a board. Just make sure it's not a magnetic pole. So a piece of wood is usually what people will use, maybe a piece of doweling, and then hand hold it. And if it's a very large piece of equipment, you may have to have somebody on this end holding it and somebody on that end holding it while you work your way up and down on the equipment. The currents aren't excessive, so this 10-to-1 step-down transformer is going to be able to give you the currents you're going to need. Now, if you do need to test for some reason to a much higher level, which is possible by some aircraft manufacturers, I recommend assuring that this wire, the remaining wire here, the spare wire, is not coiled. I have found that the impedance on the output of this thing is so low that any sort of coiling of the wire creates some inductance, and that AC current gets impeded in some ways, and you may have a difficulty getting high levels of current. So avoid coiling the wire, and that's going to be especially true when we get into induced currents into the interconnect cables. Now, concerning the electric fields into the equipment, this test requires the use of a wire that's going to have 170 volts on it. You may need to use that AE Techron 37-to-1 step-up transformer they have in order to get that higher voltage. And I also recommend maybe using a high resistance or high voltage resistor in there, kind of as a current limiting, in case something were to happen. The end of the wire touches ground or touches the equipment for some reason. Now, the best way I've seen this done is by using a high voltage high voltage wire, usually a silicone-based wire, and placing that inside, say, a plastic tube or taping it to a piece of wood or something, but assuring that you have the end of it sealed off so that it isn't going to short to chassis, because you don't want to start to inducing 170 volts of AC power in locations you're not going to be able to control. Now, I do recommend using a silicone insulated wire. This is going to come in handy when we're doing some of our other testing. It is capable, most of these are capable of handling thousands of volts, so it should provide the safety you need for high voltage on this wire. And if you're going to use a voltmeter to measure across the transformer, make sure that you're using something that has a high voltage probe. It's capable of measuring these higher voltages. We don't want to damage something because we're trying to make a measurement across the transformer of a high voltage. So proceed with caution there. Now for the interconnecting cable test. Let's talk about the magnetic field one first here. In this case, you're going to induce some pretty significant currents into a wire, and you're going to route that wire adjacent to your interconnect cable. Now, you remember I talked about if your cable is 2.8 meters long, you only have to expose 2.5 meters of that. Well, here's why. You do not need to expose the 15 centimeters on this end of the cable and the 15 centimeters at the support end or the test equipment end of the cable. So you're removing essentially 30 centimeters off of your cable. Now, in the case of DO-160, this test cable is recommended to be 3.3 meters unless you know what the distance is, but at least 3.3 meters. Well, that 3.3 meters will allow 3 meters to be exposed here. You are placing it next to the equipment, next to the cable as close as possible. So it says less than 5 millimeters. My recommendation is just to use some like Velcro straps or something of that nature. Just strap the wire right next to your interconnect cable as close as possible. Use that 10-to-1 step down transformer, the T1000, because you are going to need a lot of current. And make sure this is a high current cable. Now, one trick that I have done, and there's a couple of ways you can do this, I will tend to use things like 12 gauge speaker wire. Well, the 12 gauge speaker wire has two wires in it. So you essentially have two parallel 12 gauge wires. Well, now you're capable of carrying quite a bit more current in that 12 gauge wire if you strap those two wires together. Another trick I've done in the case where very high levels need to be obtained and maybe this transformer is inadequate, well, the AE Techron transformer is quite capable of giving you a lot of current. But let's say you have to go higher. What I would do is come out on one wire, go all the way around, and then when you get to this point, jumper that over to the second wire in that zip line and continue it around and then terminate the second wire over here. Well, now you've got two turns, but each turn has, let's say, 20 amps in it. Well, that's a total of 40 amps you're going to expose to the equipment, and you'll be able to get a higher test level as a result. These test levels are a little confusing to understand. You're going to see them in the form of, say, 30 amp meters. What that means is the total current times the length of wire that's exposed. 3 meters are exposed here. That means you need 10 amps of wire of current in that wire times the 3 meters, and now you have 30 amp meters. Why do I want to point that out? Well, what happens if you have a shorter cable here? Well, let's take a look at that. So let's say I only have 2 meters exposed here. Well, to obtain 30 amp meters, I would then have to increase the current to 15 amps in order to get my full test level. That may be the case in a situation where somebody did not make an interconnect cable an adequate length, or the support equipment is not close enough to this end, and you're not going to have enough cable that you can use in the test chamber or the test area to perform this. You will then have to increase the induced current along that path. You have to monitor how much current and report that at each one of the frequencies that are being tested. And I recommend, if you're going to have to log the frequency, use a multimeter that's capable of frequency measurements. But I tend to put it on the other side of the transformer. The reason why, this is going to be a very low voltage on this side, a very high voltage or higher voltage on this side. The multimeter is going to be able to measure the frequencies easier. The other thing is I tend to make these cables very, very long, 7, 8, 9 meters, 10 meters long. The reason why is that I don't know where I'm going to be able to expose 3 meters. It may be some remote place, plus the fact you have to find your way all the way back to the transformer. Well, I've already got 6 meters plus this distance, so that's a meter here, meter there. That's 8 meters of cable that I require just to perform this. So 9, 10 meters of cable may be what you're going to have. If you do have a shorter cable and you're capable of having this transformer somewhat close to your test equipment, you're going to end up with a lot of extra cable. Do not wrap it. Once again, that coil of wire is going to be a pretty high impedance, especially when we start dealing with category W, where you have to get up to 32 kilohertz to perform this test. Getting that high, that far high in frequency, that much current, can be a challenge if you have a coil of wire here. So keep that wire straight. If you need to serpentine it or something of that nature, that's fine. But I just recommend leaving it straight, letting it hang on the floor, whatever. Just do not coil it up. Now, similarly for the electric fields into induced current, you're going to use a step-up transformer this time. You can obtain some pretty high voltages. The category CW, for example, gets up to 5,400 volt meters. Again, voltage times the exposed length will tell you how much voltage you need in that wire. So 5,400 volt meters means you're putting 1,800 volts on that wire. Proceed with caution. Once again, this is a great place to use that silicone insulated wire, and make sure that you proceed with much caution at the end of this wire. If you have to measure the voltage and you're measuring it between the output transformer, which is grounded on the ground side, and the end of the wire, make sure that this meter is capable of measuring those very high voltages. Now, for this test, the wire is wrapped around the equipment, and the requirement is to have 3 turns per meter. Keep it about that. Don't wrap it real tight, 20 turns around there. There's no need to do that. Just three turns per meter. It's going to be 9 turns across 3 meters. That's entirely adequate. Just make sure that you do wrap it and keep the wire as close as possible to the cable under test. Again, 15 centimeters from the unit. Make sure you have some space here. 15 centimeters on this side. And mainly that is to assure that you're not coupling this field directly into the equipment or directly into the connector. That's the reason why they want some of the spacing. This side is done because, well, maybe you have support equipment that's somewhat sensitive. So we want to make sure that we're not getting the equipment, getting it susceptible because of the test that we're performing. And finally, let's talk about the induced spikes induced in the interconnect cables. We also call this chattering relay. If you notice, we have this wire wrapped around the cable once again. Well, since we're dealing with high voltages on this wire, 600 volts or higher, I recommend just using the exact same cable you had for the previous test. Might as well use that same silicone cable. You've already wrapped it around there. Just drop in the chattering relay test, and you're off and running. This is a standard, normally closed relay. There is a value we have discovered on the DO-160 committee for maintaining this test. There was some discussion about going to a test that was much more repeatable, much more predictable, such as MIL Standard 461 has CS115 tests, and that was one of the tests we were considering using. However, the committee agreed with me, and I will admit I was pushing this, that there is a great deal of value in the randomization of some of these tests. This tests arcs and sparks, and you get a real hashy noise that is likely to expose your equipment to some serious issues. So this is a good test to perform early on in order to determine whether or not you have any sort of susceptibility to your equipment. Typically, if you can get through this test, the remaining other tests, most of the other tests will probably be easier to pass. Again, the voltage measurements you're making here, they are fairly high voltage. So assure that your voltage probes are rated for that high a voltage. Most oscilloscope probes are only rated for 300 volts. Make sure you're using one that will measure at least 1,000 volts. Now, finally, there are some two things to notice. I talked about earlier that what happens if you use a shorter cable here? Well, there's no relaxation to this test. You can't drop the voltage. How would you drop the voltage to begin with? Can you use less exposed cable? Well, you'll have to for a shorter cable to begin with, and that will automatically kind of drop the voltage down. But so unfortunately, you have to do the test with the levels that are given to you. Now, we've had people talk about the fact they cannot obtain 600 volt spikes off of this relay. And there are two reasons why that may occur. One, you're not using very much cable here. Maybe you've minimized this cable length. And as a result, that shorter cable has less inductance. Now, that's fine, but it's a combination of the inductive kick from the solenoid and from the wire that wants to arc across the contacts of this relay. If you find that you're having trouble with obtaining the 600 volt spike, simply place an inductance in one of these wires, and adding that inductance to that wire will also add inductance to this relay coil, and that will increase that inductive kick through the contacts, and you will likely have a much higher voltage as a result. And that's what I've got. Thank you for listening, and I'll hand it back to you, gentlemen.